Okay, so let's continue. The next talk will be given by Dr. David Catling.
Okay, is this volume okay? Okay. So before talking about climate evolution, which is how these planets here, Mars, Earth, and Venus, have ended up so differently, at least part of that story is where their volatiles came from. Where did the ocean on the Earth come from? Did Venus once have an ocean as well? What happened to it? Well, we have to start at the beginning with the origin of these atmospheres. And the origin of the atmosphere is connected to the origin of the solar system. As Jack said, this is the issue of how these planets get their volatile substances. So we're talking about where did these volatile substances come from? Where did the water come from? The carbon, the nitrogen, and sulfur, for example. But we also have rocks from the Earth, from Mars, from the Moon, and also spectroscopic detections. And so we can talk about geochemical indicators of the origin, for example, the deuterium-hydrogen ratio in water. And then I also want to talk about Earth's earliest atmosphere. At the very beginning, what kind of atmosphere did it have? Because that's also probably relevant to terrestrial planets in general, and certainly to Venus. So the first part is, so there's 4 parts, and the first part is setting the stage. So the origin of the solar system. So there's some bit of overlap here with what Ted talked about, and also with what Jack talked about. So I'm going to go through this fairly fast because we've already met some of these ideas. And of course, the basic idea is the nebula model. Nebula, Greek word for cloud, and we start with the molecular cloud in space. This is a nice picture of the Orion Nebula. That's a scale bar of 5 light years, and this is our conceptual picture of going from molecular cloud to a planetary system. And Ted showed us a picture earlier of the trapezium in the Orion Nebula, which is these young stars. So the brightest of these is just a few million years old. These are stars and systems that are forming that we can see. And this summary is just sort of summarize what Jack talked about. So this is time in years on this axis. And up here is size. This is a schematic diagram going from dust at the micron size, planetesimals, planetary embryos, thousands of kilometers, up to planets. And this track here is roughly what happens. This is from Sean Raymond, who models terrestrial planet formation. And on his diagram, he's drawn a couple of possibilities, which is where you get rapid clumping up to embryos. This is line A. And there's also this more standard model, line B, of runaway growth that Jack talked about. And where these two things converge, you get oligarchic growth, where regions of the disk are dominated by a planetary embryo. And then several of these planetary embryos, maybe a dozen, end up as an Earth-sized planet. Whereas in the outer part of the solar system, a core that's 10 to 15 Earth masses captures the hydrogen helium directly from the nebula. And then, of course, you've got this clearing stage that Jack talked about, which is millions or 10 million years or so. The Earth's atmosphere, or the Earth, if we look at its composition, we can see that this is Earth over solar composition, and these are elements along this axis, hydrogen, helium, and other ones. And you can see that relatively the Earth is depleted in volatiles. And in particular, these ones which are circled, which are the noble gases. So neon, which is quite an abundant element, is highly depleted. This is a log scale, so this is going down by a factor of over 1 billion compared to solar. So what it shows is that, at least today, we don't have anything that looks like a direct capture of the solar nebula. So if the Earth did capture any gas from the solar nebula, then it was lost. And what we have as an atmosphere came from other things. And the other things that came from were solid materials, hydrated minerals or ice, and carbon in the form of solids, hydrocarbons, or maybe, question mark, carbonates. We could ask the question, what is a volatile? Well, basically, we're talking about substances with low melting or boiling points. So they're either present on a planet as a liquid or a gas. And for atmospheric sciences, I tend to think of volatiles as being things that form an ocean or form the air on a planet. Although there are geochemical volatiles, such as certain metals like potassium that have low melting points. That's not so much what I'm talking about. So if the Earth didn't have a primary atmosphere, meaning one made of nebula gas, then it's said to have a secondary atmosphere. And in the 1950s, people thought that this secondary atmosphere accumulated from volcanic gases, that we know that when we look at volcanoes today, we see gases coming out. Clearly, if you wait long enough, the gas will accumulate in the air. There'll be some losses from geochemical processes, but at least it must have an influence on the atmosphere. But nowadays, when we think about the way that planets form, once the Earth reaches maybe a little over a third, actually more like 40% or 50% of its mass, then the things that get accreted explode and get vaporized like a nuclear bomb. And consequently, if they contain 10% ice, say it's an icy asteroid, plus other volatile substances, those will be turned into gas during accretion. And so the atmosphere starts to form as the planet forms. And the ocean, it may not form as an ocean, but it will form as steam as the planet forms. And eventually, it will radiate to space and cool down and collapse and form an ocean. And also, some of these volatiles have returned probably to the interior because we have a tectonic system, at least on the Earth, where parts of the crust and the rigid material under the crust, which together we call the lithosphere, gets subducted. It goes back into the mantle, and things can go back. So some of these volatiles can go back into the mantle over time. Where did these volatiles come from? And why do we care anyway for astrobiology? We care because these are essential to life. Hydrogen, oxygen, carbon, nitrogen, sulfur, plus phosphorus. Okay? Sometimes people call these the CHNOPS elements. I find that difficult to say. I prefer the word sponge. These are the elements that make up 99% of a bacterium in my fingernails, and also me as a whole eukaryote. Okay? These elements are critical. Not just for the water that's inside us, but also the carbohydrates. We need the hydrogen and oxygen and carbon. Nitrogen is the structural element of life. That's what we have in amino acids and proteins. If you could magically take away the nitrogen, you would drop into a little pile of dust, like one of those cartoons. you see on TV. And phosphorus, of course, is in the genetic code in the DNA, the RNA, and also in adenosine triphosphate, the energy storing molecule. So we need these elements to make the kind of life that we have on Earth, and they need to be available and not locked up. When we look at meteorites, we can think about where they came from, the kind of asteroids they came from, and this is kind of a very basic picture of that. So if you have an undifferentiated asteroid, then it hasn't divided up into a core and a silicate mantle, a bit like a mini Earth. And if you break one of these up, you can potentially get the iron from the core. You can potentially get a piece of silicate, which we call stony, or you could get a mix, which we would call a stony iron meteorite. That's a sort of basic picture that we have of the types of meteorites. Irons, stony, which includes these chondrites, and also these achondrites. So the chondrites contain these chondrules, which, as Jack mentioned, are these, they're like miniature igneous rocks, miniature melted pieces of rock. The chondrules, a few millimeters in size, rapidly cool to melt. And there's ordinary chondrites, ordinary because most of them are ordinary chondrites, over 95%, and carbonaceous chondrites that are more carbon-rich, relatively speaking, and look like it too. And then the ones that don't contain chondrules include things like the Martian meteorites, pieces of Mars. But when we look at the composition in detail, the carbonaceous chondrites, these pieces of asteroid, can be very rich in water, up to 20, maybe 25% H2O, and they have carbon, a few percent of organic carbon. They have nitrogen as well. And so if we made the Earth of carbonaceous chondrites, we would have enough for 600 oceans. So there's no problem if you can bring in some of this material, just a fraction of it, to have enough water for an ocean. Okay? If you bring in 1%, you've got 6 oceans worth from carbonaceous chondrites. Ordinary chondrites contain less water, less nitrogen, and less carbon. So if you made the Earth of ordinary chondrites, you'd just have 4 oceans, which is below some of the estimates for the water in the Earth. If you've got 1 ocean on the surface and maybe 5 oceans in the mantle, which is at the upper end of some estimates. People talk about 2 to 5 oceans in the mantle. So we need some planetesimals, probably with carbonaceous chondrite material. And both Ted and Jack talked about the condensation sequence going from, this is temperature, and this is going down in temperature in Kelvin. And as you go down in temperature in a solar nebula model, these are the things that condense. Okay? So at 1360 Kelvin, that's when iron and nickel iron will condense. These are core-forming materials in the terrestrial planets. Then you have rocks, silicate materials. These are minerals you find in rocks. And then you get hydrated minerals at about 500, few hundred Kelvin in the solar nebula. They could also contribute water. And then below that, these are ionic substances. Below that, you get molecular substances, water ice, colder still, ammonia ice, methane ice, and maybe even nitrogen ice if they're hydrated. And in general, we can think of this as being the inner nebula. This is the outer nebula beyond the ice line. That this John Lewis model at least explains, broadly speaking, the gross differences between the inner and outer parts of the solar system that we observe. And the break point is where water condenses. It's called the snow line, it's called the ice line, and it's also called the frost line. So various words for that picture. And this is the picture. So here's the accreting rocky material. Here's the accreting rock plus ice beyond the ice line, frost line, snow line, and a lot more solid material out here if you can accrete the hydrogen. If hydrogen and oxygen can form into water ice. So a key point then is that as was said before, is that the material in here has to get its, if we have a planet with an ocean, it has to get that water from outside where it is. How does that work? Well, this is a schematic picture, but there are various papers by John Chambers, Morbidelli, Sean Raymond for models of the terrestrial planet formation. And so here's Jupiter. It forms within 10 million years. As it does so, it disturbs material. Here, some of this icy material beyond the ice line gets scattered into the inner solar system, and these rocky planets can accumulate, at least in part, some of this icy material. And if some of this is carbonaceous chondrite material, or even some ordinary chondrite material, this contains some water, some nitrogen, and some carbon, some of these essential elements, these volatiles. So Jack showed you a picture of one of these simulations where this is color-coded. So this is log of the water mass fraction. This is 0.1% here, water, 1% water, 10% water, basically representing what we think the planetesimal composition might have been in terms of water abundance in some kind of initial state before these planetesimals, there's 2,000 of them here, grew into the rocky planets. And so this is a simulation. On this axis is eccentricity. This is, if it's 0, it's a circular orbit. If it goes up to unity, that's a parabola. You've broken the ellipse beyond unity. And so this is a simulation from Sean Raymond. And look at what happens to these things. And here's the time marker. Right, where are we? So as time goes on, gravitational perturbations pump up the eccentricity. There are bodies which are growing and which eventually begin to dominate their parts of this disk of material. And in particular, the color code is changing. So some of these things which were in the part of the original disk that were dry are now getting wet because they've accumulated some of the wet material.
That is Jupiter.
This thing is Jupiter. You'll see it's not moving very much because it doesn't get perturbed by it. It's perturbing these things and it doesn't care so much. And so after 200 million years, we have some terrestrial planets. They may have started off in a dry region, like 1 astronomical unit, but they've accumulated some of this material that has more water from beyond the ice line. And so this is a random process, and Jack showed you how even tiny variations in the initial conditions can result in whether you get a planet or not. But the variations can also result in whether you get a dry planet or a wet planet. So there's a large element of chance as to how much water you get. Okay, how much bulk water does the Earth have? The estimate is something like 0.04 weight% total water. So actually, all we need is for it to be slightly blue, about here. not yellow maybe, but just here would be fine. Actually, maybe a bit into the yellow. So this thing here is probably wetter than, we don't know exactly, but probably wetter than the bulk Earth. And if you bring in the water from these kind of bodies in the what now is the outer asteroid belt, then when we look at the meteorites, we can say, well, if they're water rich, they probably also bring in a fair amount of carbon and a fair amount of nitrogen too. Actually, the amount of nitrogen turns out to be a problem. We don't have that much nitrogen. There's 1 bar in the air. On the Earth, there's probably another 2 bars in the mantle. So you have to do something with the nitrogen. And what people usually do is they stuff it in the core and say, well, you know, there's a 100 bar in the core or something like that. Either that or it has to be lost somehow. But you end up with, usually in this kind of situation, you'll end up with an embarrassment of riches when it comes to some of the other volatiles. If you end up with enough water, you have an embarrassing amount of nitrogen. But most people usually don't talk about that. And so then you end up with the solar system that we know, with the planets. And this is a funny picture. I was looking at, I downloaded this from online. I realized there's Saturn and Uranus have gone missing. But anyway, we have the Kuiper Belt beyond Neptune, and then the Oort halo cloud, a long-period comet, and so on. And these are the objects, of course, that we can look at this debris that didn't get incorporated into the planets to give us clues, as we did earlier. And we can also look at the planets themselves. So if we're trying to trace the origin of the water, we can look at hydrogen and deuterium, for example. So what does the deuterium-hydrogen ratio tell us about the origin of the Earth's oceans? I think the balance of evidence shows us that it probably came from the region that's now the outer asteroids, but it could have been modified by a smaller cometary component. So when we look at long-period comets from the Oort cloud, the D to H ratio in the ocean is about half that observed in comets like Halley, Hyakutake, Hale-Bopp, and other Oort cloud comets. The dynamics is not particularly favorable for comets. There have been estimates, something like 1 in 3,000 hit. But there are so-called Jupiter family comets, Kuiper Belt comets, and they actually have a D to H ratio which within error bar is the same as seawater, but their nitrogen isotope ratio doesn't match. Whereas the nitrogen isotope ratio in the asteroidal material does match the Earth, broadly, and so makes sense that as well as the D to H ratio, so it makes sense that this is the source of the volatiles. When we look on Mars, and we look in the Martian meteorites, sometimes called SNC meteorites, Shergottites, Naquilites, Chassignites, types of Martian meteorite, they cluster actually around 2 times Earth, which is the long-period comet value. So it looks like Mars may have actually accumulated, been hit by a long-period comet, and may have a veneer of that material. But actually there's a dispersion, quite a large dispersion of the D to H ratios in Martian meteorites, going from seawater values up to the long-period comet values. So Mars is not quite so clear. Is this not working? Okay. Okay. And let's see, so Venus has a very high D2H ratio, over 100 times the Earth, but what does that mean? It just means that it's, at some point in its history, could have been early, could have been later, it has lost hydrogen relative to deuterium. And you can interpret that as being a lot of water loss early in its history, but it could also happen later on, and it doesn't have much water anyway in its atmosphere, just about 30 parts per million, and even is losing hydrogen today. So it could be replenished occasionally by the odd comet impact, and then it could lose hydrogen relative to deuterium. So you can interpret it as water loss, it certainly is, but it doesn't necessarily mean that it was lost early on. But the models would suggest that Venus got the bulk of its volatiles, just like the Earth, from the region beyond the ice line, the outer asteroid belts. It does have some strangeness to it, though, the atmosphere. The noble gases are quite a lot, neon and argon, are more abundant than the Earth, which is suggestive of some cometary component to its atmosphere. So if we plot the D2H ratio on this axis times 10 to the 6, and we do a histogram of, these are ordinary chondrites, carbonaceous chondrites, and let's see, the vertical gray lines show the Sun, Earth, and comets. So here's the Earth, and these are actually only the Oort cloud comets, the long period comets. But you can see that there's a nice match between the Earth and carbonaceous and ordinary chondrites overall in this histogram. If we look at the rocky planets, Earth, Mars, and Venus, and we plot, here's different elements plus water. These are going in this direction. We have increasingly volatile elements and substances. And this is a logarithmic axis. And if it's 0, then your solar abundance. And this gray are refractory elements. These are geochemical volatiles, things like potassium, zinc. And these are, I'm calling atmophiles. So these are things that tend to vaporize or tend to form substances that go into an atmosphere. Atmophile loves being in an atmosphere. And what you see is that even when you get to the geochemical volatiles, for the planets, they're somewhat depleted. So this is going down an order of magnitude each square. But when you get to the atmophiles, then they're very depleted. Even this is a carbonaceous type of carbonaceous chondrite. Even that's depleted relative to solar. If we look at the Earth, which are the triangles, then this shows increasing depletion as we go to more volatile substances. If we look at Venus, you'll notice this big step down with water, that something happened to Venus to make it lose a lot of water. It's a bit of an odd man out here. If we look at Mars, that's the circular one, and it sort of follows a pattern a bit like the Earth, except it's more depleted in the atmophiles by maybe an order of magnitude or 2 compared to the Earth. Whereas at least Venus is similar, apart from the water, to the Earth in its depletion of volatiles. And what this is showing us is not so much something about the origin, although partly it is, but it's showing us that these planets had different evolution of their volatiles. So the depletion of water on Venus is because its atmosphere is thought to have gone through something called a runaway greenhouse effect. And as I mentioned the other day, it's so hot on the surface of Venus that it can't even have, it's impossible to have liquid water. And the depletion of volatiles on Mars by a couple of orders of magnitude with respect to the Earth also shows that something happened to Mars, that it probably lost air to space. Today, the surface of Mars, the surface pressure is down by a factor of 100 or so below that of the Earth. So it has a very thin atmosphere. There are other clues about what happened to these planets if you look in a bit more detail. So for example, Jack mentioned that argon-40, the almost 1% of the air that we're breathing right now, is argon, most of it argon-40, which is produced by radioactive decay from potassium-40 with a half-life of 1.25 billion years. If we look at that on Venus, we find actually that particular isotope, which has gradually accumulated in atmosphere, that on Venus it's only a quarter of the argon-40 found in the Earth's atmosphere, which is a little bit puzzling because we think of the Venusian atmosphere as being a lot thicker and more volatile rich than the Earth, but not argon-40. And perhaps an explanation is that Venus is actually not, in some ways, as efficiently outgassed, at least for this radioactive isotope that's formed from materials in rock, minerals. So that if it did have a period when it was once habitable, perhaps had an ocean, perhaps had volcanism, it couldn't have lasted that long, because otherwise it should be more like the Earth with its argon-40, you would think. In contrast, on the Earth, we've had plate tectonics. We still have active volcanism today. It's still melting rocks and pumping out argon-40 into the atmosphere. Okay, so that sort of covers some parts of the essentially the key points about what we think of the origin of the atmosphere. But what was the earliest atmosphere on the Earth? I mentioned that the atmosphere formed during accretion. Here's a plot I made of time after solar system formation. Remember, there's a 1 million year error bar. This is millions of years ago. Jack had 4, 5, 6, 8. I'm having 4, 5, 6, 7, since there's a 1 million year error bar. I find this easy to remember. 4, 5, 6, 7. Goes up 1 digit at a time. And this is 0.1, let me see, 100 million years after this time, which is the date of calcium aluminum inclusions, the oldest solid material in the solar disk. So this is after that. The calcium aluminum inclusions are up 0 point here on this axis. And these are estimates from the literature of various events. Chondrule formation, proto-Earth formed, moon forming impact, and the age of the Earth. So about, I don't know, roughly 4,500 million years ago, but there's error bars associated with this. And the Earth is growing here, and maybe somewhere along this line, maybe take the middle point here, a few million years, 50% of the proto-Earth is formed. At that point, the things smashing into the Earth can volatilize and degas, and there would be a degassed atmosphere on this proto-Earth here, actually probably before the moon forming impact hit. Well, there's been some models of this, and what you get is a steam atmosphere, because water can make up a large percentage of some of these impactors. And so this is time in millions of years. So after several millions of years, about 10 million years roughly, you can get a very high surface pressure, which is mainly a steam atmosphere, but there could be other gases in there too. It depends upon the chemistry of the impacting object, whether it's an iron-rich body or mainly a silicate body, and the various things that it contains. But there'll certainly be a lot of water vapor. that ends up as steam. So imagine a steam atmosphere with a surface pressure around about tens or 100 bar. As the proto-Earth is growing, this is its radius, and it's reached about 40 to 50%, and then you get a steam atmosphere. Well, I mentioned water vapor is a very good greenhouse gas. So if you have tens or 100 bar of water vapor as steam in the atmosphere, you have a really good greenhouse effect. It's so strong that you melt the surface. So we also have a molten surface below a thick atmosphere of steam as the planet is growing. And this is actually an interesting situation, because I mentioned the other day that we have in the modern atmosphere, we have a window where infrared photons from the surface can escape directly to space. But actually, if we imagine we start with this atmosphere and we added some water vapor to it, or we warmed the Earth so it could hold more water vapor, and warmed it more so it could hold more water vapor, eventually there's no longer a window. You've closed the window, and actually your atmosphere becomes so moist that now above your surface, this part of the atmosphere is optically thick, opaque to essentially all of the infrared wavelengths. And now it's like the Earth has a photosphere. Like in stars, you can only see down to a certain depth. But the properties of this photosphere are set by water vapor. So this is infrared, and this is opaque in this very wet atmosphere. And this infrared optical depth is approximately unity. And if you look down at this planet, you couldn't see the surface in the infrared. It's coming from a sort of infrared photosphere. This is called the runaway greenhouse effect. And what it is a limit set by the properties of water vapor on how much flux you can have from the planet. So for the Earth, this limit, this runaway limit, is approximately, I mean, there are different calculations in the literature, but it's something, roughly rounding, it's something like 300 watts per meter squared. Okay? In other words, no matter how hot this surface is, you cannot lose more than 300 watts per square meter from this situation. This is okay for the modern Earth. We don't have a runaway situation because the incoming radiation, I said in the previous lecture, was an average of 240 watts per square meter. It came from a calculation where I looked at the solar constant, and I said we divided by 2 for night and day, we divided by 2 for glancing angles, and we modified by the albedo, which was 0.3, and that got the average solar flux on the planet as 240. If we move the Earth today, we're God, we can do what we like. We move it closer to the sun. If we moved it to the orbit of Venus, we'd get about twice the flux. So we'd get 480 watts per square meter, and our planet would become like this. We'd have a runaway greenhouse effect. That means that there's more incoming solar radiation than we can get out. That means the temperature gets hotter and hotter and hotter until all of the ocean evaporates, the surface begins to melt, and the atmosphere becomes so hot up here at altitude that it begins to be so hot that it radiates through near-infrared windows. And then it comes into balance. But it's a nasty balance because the surface is molten. in the runaway greenhouse effect. But the definition of a runaway greenhouse effect is it's a limit on the outgoing infrared radiation set by the properties of water vapor and the properties of the planet. Depends on gravity as well, if you do the calculation. So this is what happened to the proto-Earth. The proto-Earth had a runaway greenhouse effect, and the surface melted, and then it's able to radiate from the upper atmosphere, come into some bounds, and at that radiation bounds, it's stuck with a molten surface, actually a magma ocean. So it goes very deep. The magma ocean is also caused by the energy deposited by the impacts themselves, as well as this runaway greenhouse. But it can't last forever. It will keep radiating away to space, and eventually this steam atmosphere will collapse and make an ocean. So this is the evolution of Earth's nasty early atmosphere, according to Kevin Zarnley. And this is time in years on this axis. This is temperature. This is the surface temperature. Let's see, this is the period of a runaway greenhouse effect. And these are reservoirs, so some of these things like the CO2 here is 100 bars. There's also a lot of carbon dioxide as well as steam in the early atmosphere. The steam collapses first to form an ocean. Let's see, where is this steam? It's here, and then it collapses to an ocean. And then afterwards, the CO2 dissolves in the water and it reacts with rocks. So the very earliest atmosphere is rock vapor. Then for about a few million years, we've got a magma ocean, runaway steam greenhouse. Then up to about 100 million years, where we've got the collapse of an ocean. It's quite salty because in the early atmosphere, there's also things like sodium and chlorine. So we have a salty ocean fairly early on. Then a lot of carbon dioxide, but that's removed by being soluble in the ocean, reacting with the crust. And then for the first billion years, we have something called the Hadean atmosphere. That's an eon of Earth history. So the eons of Earth history are from, this is 4.5 billion years ago up to 4 billion years ago. This is the Hadean. Then up to 2.5 billion years ago, we have the Archean. So this comes from Hades, hell. Archean comes from Greek, enarche, meaning in the beginning of life. And then from 2.5 billion years ago up until 541 million years ago, it's called the Proterozoic eon. And during this period, zoic comes from zoas, meaning life, and this means early life. And then we've got the period, the eon that we're in, and that's called the Phanerozoic. And this means life. This means phaneros means visible in Greek, which means visible life, because there's lots of animal fossils all in this eon. We don't know much about the Hadean. And when we talk about, this thing settles down to some kind of atmosphere with an ocean, it happens rapidly. We're only talking about the first 100 million years or so. And for most of the first billion years, we don't really know what this Hadean atmosphere was like because of the lack of a rock record. The oldest sedimentary rocks, and they're not very good ones, they're messed up, they've been heated and pressurized, are, that pen doesn't work very well. The oldest sedimentary rocks are about 3.8 billion years old in Greenland. And then we have some clues about, not very good ones, but we have some information from chemistry about the Archean atmosphere, the Archean ocean. Before that, we don't have a sedimentary rock record. And so our knowledge of the Hadean atmosphere is shrouded just through lack of data. And there's a lot of speculation about what it was. And some people, we don't even know the surface temperature very well. It may have been cold. There's a group of people who argue that it was a cold period. There's other people argue that it's a hot period. This is also a period of great interest because in the Hadean is probably when life, or the beginnings of life, happened. Because by the time you get to the Archean, even in the rocks in Greenland, there's carbon isotope evidence that there was probably life around. So there are flakes of graphite that are enriched in carbon-12 by about 2%, which is roughly the carbon-12 enrichment you expect from biology. So the idea is that there were things living in the ocean, they sank to the bottom, the carbon got turned into graphite. These are not very good rocks, but at least there's something there. And this is the oldest evidence for life, 3.8 billion years ago. Now, this is a picture of this period from the beginning of the Earth after the moon forming impact up to the modern day. And it's possible, some people also talk about, as well as accretion of material that formed the volatiles, that there may have been a proto-atmosphere, some capture of nebula gas, but if there was, it was lost. And there also may have been other material that came in later. But the modern system recycles volatiles through subduction and degassing, volcanoes, subduction. In the Hadean, there was also the big lunar craters imply that about 100 kilometer sized bodies and thousands of 10-kilometer sized bodies pelted the Earth. Okay? And in fact, the lunar basin ages derived from the Apollo astronaut rocks. There's about 400 kilograms of rocks that were brought back by the Apollo astronauts from the moon. And the radiometric dates cluster around 3.9 billion years old. There's some debate about whether there's actually a larger range than this, going back to 4.1 up to a bit beyond, maybe 3.7 or something. But this is what's called this late heavy bombardment, that there may have been a spike in bombardment. And I think it was Ted that mentioned the Nice model, that there's a model for why that may have happened due to the rearrangement of the giant planets, a rearrangement of the giant planets. But in any case, out of these big impactors, there would be rare ones. And if they're larger, or the same size as 500 kilometers, they would vaporize the entire ocean during the Hadean. And statistically, maybe 1 to 4 such impactors should have hit the Earth after the moon-forming impact and up to as late as 3.8, 3.9 billion years ago. Well, this would be bad news if life got started to vaporize your ocean, or even vaporize a fair proportion of it. And so, in the late 1980s, people speculated that this may explain something on the tree of life. So we've seen this before. It's the last common ancestor. At the root is the bacteria, archaea, and eukarya. And if you look close to the root, you see thermophilic organisms. Organisms that like to live, they actually function best in their reproduction at warm temperatures, so 80 degrees Celsius. And so you could say your insert lots of greats, grandmother was a thermophile. Okay? if you go down this path, things around here are thermophiles. But possibly this is just an artifact. It could be that the last fairly big impactor pruned a tree of life, and the only thing that then lived, or was able to live, were thermophiles below the ground. Because as you go down through the crust, it gets hotter, like in a mine shaft. And so the thermophiles would be protected from the effects of a large impact. And life would start again. But the root would be thermophilic. So it may explain this distribution, why it is that there are thermophiles down here. Another connection to life is a question of whether there was something called a Miller-Urey atmosphere on the early Earth. What is a Miller-Urey atmosphere? It comes from an experiment done in the 1950s in the lab where a reducing atmosphere, meaning one hydrogen rich that I talked about the other day, naturally forms organic molecules that can then be a seed for biology. So the Miller-Urey experiment was this mixture of gases in a flask. There were sparks to simulate lightning, a condenser to collect the residue. Here's your ocean in a flask. And in this experiment done by Stanley Miller, who was a graduate student of Harold Urey, who was a Nobel Prize winner, he discovered deuterium that we were talking about earlier. That was discovered by Harold Urey. They did this experiment at the University of Chicago, and they found that this mix of gas with the lightning, and also you can put in ultraviolet light, that will synthesize molecules. It's just like what happens, a bit like what happens in the reducing atmospheres of the solar system. In the atmosphere of Titan, or in the atmosphere of Jupiter, Saturn, Uranus, Neptune. They all form organic molecules from essentially methane and hydrogen and ammonia. But the essential assumption here is that you need a hydrogen-rich mixture. This works best if you have a reducing atmosphere. But the problem is that if you have a planet like the modern Earth, if we go to a volcano, most of the hydrogen is coming out as steam, as water vapor. There's a little bit that's hydrogen. Most of the carbon is coming out as carbon dioxide. There's a little bit of carbon monoxide, but less than 1%. So this is not a Miller-Urey atmosphere. And this kind of atmosphere, if you stuck it in the flask, put that in here, the amount of organic molecules you make is extremely small or maybe negligible, depending on your exact mix. The kind of chemistry of the mantle and of the interior of your planet affects the gases coming out through volcanoes. So if you have iron, metal, that's a very reducing mixture in the solid planet. That gives rise to reducing, by the chemistry of the way this works, it gives rise to a very reducing mixture of gases. Unlike this situation after the core formed, so the iron metal sunk by gravity to the core on the proto-Earth. And this process was fast, tens of millions of years. So only the very earliest atmosphere over here for tens of millions of years would have been really hydrogen rich. It's possible that there was some chemical evolution during the Hadean that made this more hydrogen rich than subsequently. We don't know for sure. But on average, people assess this evidence to not be very favorable for a milli-URI atmosphere, but it doesn't exclude it completely. What we think of is that the modern atmosphere is weakly reduced. There's some little bit of hydrogen and methane that come out of volcanoes. But what's really good for forming organic molecules is strongly reduced. In other words, very hydrogen rich or rich in molecules that contain hydrogen. And this actually is a list of a typical volcanic gas mixture. So mostly water vapor, some fraction of carbon dioxide, but very little of the reducing gases. And you want to be in a reducing environment because it helps to form organic molecules. So people say, well, that doesn't really matter perhaps, because there are local environments that are reducing. So for example, even today, when we look at the hydrothermal vents, where warm water circulates through the ocean crust, then you can find more hydrogen-rich environments locally. We can look at other planets. We have Martian meteorites, samples of Mars. Geochemists look at the partitioning of redox-sensitive elements, such as europium, and they come up with estimates of how reducing that mantle is of a different planet. And there's a spread. The error bar is several orders of magnitude uncertainty. But overall, it seems like Mars' upper mantle may be quite a bit more reducing than the Earth's. And if that's so, then early Mars might have had the kind of atmosphere where organics were forming just abiotically on the surface and would have rained down to the surface of early Mars, like they do on Titan today. So that may mean that if this is true, this may mean that there was the possibility that organics could have been produced on early Mars, and it may have been a favorable habitat for life on Mars. Today we have a system that recycles volatiles. So for example, in July, I was in Japan, and Japan is this situation. It's an island arc volcanic system. And I was on the 11th floor. My hotel room was the 11th floor. And I woke up at night, 4:30 a.m. I looked at the clock. And I thought, oh no, I got a room with really noisy neighbors. And then I realized I was moving. And it was an earthquake. It was only 3 or 4 on the Richter scale. It was 6.8 off the coast. But this is because going underneath Japan, there's a subducting plate, and this was causing an earthquake on the 11th floor of my hotel in Tokyo. And this is island arc volcanism. Then there are mantle plumes. This is the situation with Hawaii. Hawaii is an island like this, sits above a mantle plume. And there are other places like the mid-ocean ridge of the Atlantic Ocean. So that's at the bottom of the ocean where the plates are spreading apart, and there various gases are being released. They tend to be more reducing, hydrogen sulfide, methane coming out here and off the axis as well. And then, of course, there are continental volcanic arcs. I live in Seattle. There's a big volcano I can see on a clear day called Mount Rainier, 14,000 feet high. And there's also Mount St. Helens as part of the Cascade Range on the west coast of the United States. And that has, so when I'm standing there in Seattle, I know there's a big plate going beneath my feet, very deep, doing this. But actually, these earthquakes, although they're scary, they're useful on a long time scale, because the carbon dioxide gets trapped into carbonate rocks, and sucked out of the atmosphere over millions of years, but then it comes back again, and the atmosphere gets replenished. And so there's a cycle. And also, some of the sulfate in the ocean goes down a little bit, goes down as calcium sulfate and comes back up as sulfur dioxide. So sulfur also cycles around, and so does water. Water hydrates the crust, hydrated basalt. This is an iron magnesium rich rock made of many minerals called basalt that comes out and makes up the ocean crust, gets hydrated by seawater, but that comes up again, it gets hot and comes up through these systems. So plate tectonics helps to maintain the habitability of the Earth, and I'll talk more about that in the next lecture. Let me summarize what I've said so far. So, to summarize, this lecture was in 4 parts, and the volatiles on the rocky planets were mostly acquired as solids from regions in the solar system through accretion that took 100 million year timescales. To get the volatiles, you needed solids from beyond the ice line, so the region of the outer asteroid belt, for example. And we can, both models and the geochemical data support that source of the volatiles. That doesn't mean there can't be a cometary component. It just means that it is a small, relatively small component, 10% or something. And we also looked at the lack of atmophiles. These are elements that like to form atmospheric gases, and the different atmophile patterns on Venus, Earth, and Mars, and also carbonaceous chondrites compared to solar. And what that indicated was the very different fates of these atmospheres. Venus lost a lot of water, there's no doubt about it. And then I talked about Earth's earliest atmosphere, the first billion years, and at least in the first 100 million years, it was an atmosphere inhospitable to life, with a steam atmosphere followed by a thick carbon dioxide atmosphere. But eventually it settled down after that 100 million years into some kind of atmosphere that's poorly constrained, probably a lot of nitrogen, probably some level of CO2 that was dominating the greenhouse gas inventory of the Earth. The sun at the time was fainter, so whether it was a cold planet or a hot planet, we don't really know. We know that oceans were present. There's evidence for that through the zircons, but poorly constrained. There probably was not a strongly reducing atmosphere like the Milli-Euro experiment, but it's not completely excluded simply because we lack data. But the data that we do have is not very suggestive of that kind of atmosphere. It suggests that outgassing volatiles tend to be quite oxidizing. And that's it for this lecture, so I'm happy to take questions.